The following is a special lecture titled Prime Numbers and the Mathematics of Cryptography. The lecturer is Professor Patrick Balls, Assistant Professor of Mathematics at the University of North Carolina at Asheville. Professor Balls received his B.S. from the University of Denver and went on to earn his M.S. and Ph.D. from Vanderbilt University. Professor Balls has been well recognized for his excellence in the classroom. In addition to being the recipient of a Teaching Council grant in 2007, Professor Balls has also been nominated in each of the past 3 years for the University of North Carolina at Asheville's prestigious Outstanding Teaching Award.
Hello, my name is Patrick Balls, and I'm an Assistant Professor of Mathematics at the University of North Carolina, Asheville. I'm delighted to be with you here today to say a little bit about a topic from one of my favorite branches of mathematics, number theory. Number theory is the study of properties of the integers, or whole numbers. And one of the reasons I find this topic so fascinating is because many of the simplest and most elegant results in number theory are very easy to describe and understand, but also incredibly difficult to prove, and therefore it makes it a very deep and mysterious topic to do work in. The topic I'll be addressing today is one dealing with prime numbers. You may be familiar with this topic already, but if you're not, we'll begin by giving a definition and some examples of prime numbers to make sure we're all on the same page. After that, we'll look at a brief history of prime numbers, asking some various questions about them. How many are there? Do we know where they live and where to find them? And how do we go about computing prime numbers in the first place? We'll survey some of the people who have proven results about prime numbers and see what kind of understanding we have about these numbers. After that, in order to try to convince you that there's more to prime numbers and number theory than just beauty and elegance, I'll move on to an application of prime numbers in the realm of cryptography, the science of secrecy. It turns out that prime numbers play a fundamental role in an algorithm called the RSA cryptosystem. This is a means by which sensitive information can be encoded so that when it's transmitted across an unsecure network like the internet, it can still remain secure even if intercepted by a third party. Again, prime numbers will play a fundamental role in this and therefore will be useful as well as beautiful. And at the very end, we'll just wrap up with a brief description of the security of the RSA cryptosystem. How is it that this method will remain secure as a means for encoding information safely? So to begin with, let's start our journey talking about prime numbers. What is a prime number exactly? Well, to understand primes, we have to understand what a divisor is. If I give you two whole numbers, say d and n, you can tell if d is a divisor of n by just dividing d into n in the ordinary grade school way. If you divide n by d and you obtain no remainder, dividing as you would in elementary school, then we say that d is a divisor of n, or that d divides into n. We'd also say that n is a multiple of d, but for this talk we'll look mostly at the point of view of the divisor. That's the definition of a divisor, and we can use this to define what prime numbers are. A prime number p is any whole number bigger than or equal to 2 which has no divisors other than itself or 1. So p is greater than or equal to 2 and has no other numbers besides 1 and itself, the obvious divisors, dividing into it. Now it's very easy to list some of the first prime numbers. For instance, 2, 3, 5, 7, 11. These numbers are all prime, as you can easily verify by noting that they have no divisors other than themselves or 1. On the other hand, a number like 20, for instance, would not be a prime number because it has divisors 2, 4, 5, and 10 that are not trivial, i.e. they are not equal to the number itself or to 1. So that's really it. It's a very simple and elegant definition, and so it might come as no surprise that people have been investigating prime numbers for centuries. In fact, our historical journey will take us back 2,300 years to the time of Euclid of Alexandria. Euclid was a mathematician who is best known for his monumental work of mathematics called the Elements. In this work, he began with a few basic propositions. They were called axioms or postulates, whose truth was considered so self-evident that there was no proof required. We just assumed they're true. Working from those postulates or axioms and using some basic rules for logical deduction, Euclid was able to amass a pile of mathematical results on topics ranging from number theory to algebra and geometry. Now, what concerns us here is not so much Euclid's work in geometry and algebra, but of course in number theory. About prime numbers, he was the first to ask the question, how many are there? And it turns out there are infinitely many primes. Euclid was the first to prove this, and there have been many that have proven it since his time. Many of the arguments that have come after Euclid have been very sophisticated and have used very complicated, high-level mathematical methods, but Euclid's proof is so simple and elegant that we can recover it right now. So we're going to go ahead and prove Euclid's statement that there are infinitely many primes, and to do so, we just need to make the following basic observation. If I give you a whole number n, then that whole number n is either going to be prime or have a prime divisor. This is a very easy statement to prove. If n is prime, we're done, because that was one of the possibilities that I allowed. If n is not prime, however, then by definition, there is some divisor other than the number n that divides into it. We'll call it d. So if d is prime, we're done, because then we've found our prime divisor. On the other hand, if d is not prime, then we can divide it further, obtaining another divisor, which in turn is a divisor of the original number n. So one way or another, we can keep subdividing into smaller and smaller numbers, and either we encounter a prime divisor or we keep going. And eventually we will find a prime divisor, because eventually there will be nowhere to go. We've divided into the smallest numbers possible. So every number is either prime or has a prime divisor, and it is upon this observation that our proof will rest. The method of proof that we'll use to prove this proposition is called a proof by contradiction. We're trying to show that there are infinitely many primes, and to show this, we will assume that the opposite is true, that there are only finitely many primes. We want this statement to be false, so from it what we'll do is we will derive a statement that is obviously false. And if we can start with a statement and from it derive something that is evidently untrue, that means the statement we began with had to be untrue as well. So we'll assume there are only finitely many primes, and if that's the case, then we can list them. We'll say P1, P2, and so forth through some Pk are the only primes that there are. Working with those finitely many primes, we can construct a new number. We'll call it n. n is defined by taking the product of those primes, P1 times P2, and so forth through Pk, plus 1. The plus 1 is very crucial because it's the means by which we will show that we have too few primes in our list. So n, again, is P1 times P2, and so forth through Pk, plus 1. Now let's attempt to divide n by P1 and see what happens. P1 divides into the first term in n evenly. That is, when we divide P1 times P2 and so forth through Pk by P1, we obtain an even quotient, P2 times P3 times and so forth through Pk. However, that plus 1 on the end is crucial because we can't divide into that plus 1. That guy gets left over as a remainder, and therefore P1 did not divide evenly into the number n. Therefore, P1 is not a divisor of n. The same argument would work equally well for P2. There was nothing special about P1. It would work for P2, P3, and so forth through Pk. None of the primes in our list turns out to be a divisor of the number n we've just constructed. And this is a problem, because we assumed we had all of the prime numbers in our list. But since n is not divisible by any of them, that means that either n itself is prime or has a prime divisor that was not in our list in the first place. Either way, we missed a prime. So our list was incomplete, and this is the contradiction we were seeking. Therefore, we could not have listed all the primes in some finite list. There must be infinitely many of them. But if there are infinitely many, we might be wondering, where can we find them? Is there somewhere in the integers where they're hanging out more densely than elsewhere? If we look at the list of integers, if you recall, I named some of the first primes earlier, 2, 3, 5, 7, 11, 13. These numbers are all prime. Notice that if you look at the first integers from, say, up to 10 or 20, almost every other integer is prime. So the primes are very dense at the very beginning of the integers. And this makes sense if you think about it, because if the numbers are small, if the number n is small, for instance, there are a very small number of potential divisors for n. There's not a whole lot to divide into it, so it's highly likely that our number is going to be prime. However, as n gets larger, we see that there's a much larger number of potential divisors, and therefore the larger the number n is, the more likely it's not going to be prime, because we'll more than likely be able to find a divisor that divides into it. So we suspect that the numbers n, as they grow larger, are going to be less and less likely to be prime, and therefore the primes will be more sparse among the integers. this is a good observation, but can we refine it? Can we make that more precise? Exactly how many primes do we expect to find? Now, it turns out that about 200 years ago, the German mathematician Carl Friedrich Gauss, perhaps the greatest mathematician to ever live, looked at massive tables of prime numbers that had been compiled before him, and with the knack that he had for recognizing patterns, was able to notice that there was a pattern in the distribution of prime numbers. He noticed that as n grew larger and larger, the number of prime numbers less than or equal to the number n grew closer and closer to n divided by the logarithm of n. Now, it's not important that you know exactly what the logarithm is. Don't worry if that's unfamiliar to you. What's important is that we can predict with very good certainty how many primes there will be up to and including a given number n. Gauss conjectured, in fact, that the number of primes less than or equal to a given number n, he denoted this by pi of n and called it the prime counting function. The number of primes less than or equal to n, as n grew increasingly large, was indeed closer and closer in ratio to n divided by its logarithm. And I've actually compiled a slide on which you can see I've listed both the number n, the value pi of n, this is the prime counting function that gives us the number of primes less than or equal to n, and the ratio n divided by logarithm of n. I've also listed the ratio of those last two quantities, so you can see that this ratio gets closer and closer to 1 as the number n grows larger and larger. That is, as n increases, the ratio between these two values, the number of primes less than or equal to n, and this function n divided by its logarithm, grows closer and closer to 1. These values are very close to one another, therefore, and we can predict with good certainty how many primes there will be. But this isn't exactly the same thing as listing the primes, and that's something we might like to do. So how do we go about testing whether a given number is prime, or listing the primes systematically? This we can do as well, and there are many techniques to do so. Many very sophisticated arguments depend on some high-level mathematics that I don't have time to get into right now, unfortunately. But there is a very simple method of computing primes that was available to a contemporary of Euclid named Eratosthenes. You may be familiar with Eratosthenes through his experiment in which he was able to provide a highly accurate estimate for the circumference of the Earth. By taking a rod and jamming it into the ground, he was able to measure the length of the shadow cast by the rod at high noon and compare that length with a length of a shadow in a similar experiment performed several hundred miles away in ancient Egypt. By knowing the distance between these two locations and by comparing the lengths of the shadows cast with a little bit of trigonometry, he was able to extrapolate a figure that gave an estimate for the circumference of the Earth passing through those 2 points. And this circumference, his estimate for this circumference, was astoundingly accurate to within 15%, which was amazing considering the rudimentary nature of his experiment. But, of course, this is all besides the point from our point of view. We're mostly concerned with what Eratosthenes had to say about primes. Now, he invented the sieve, which is a means by which he was able to sieve or sift out the prime numbers from all of the other numbers. And it begins like this. Let's say we want to find all of the numbers that are prime from 1 to some number n. We first write them all down, and then we collect the number 2 and we keep it. We put it aside because we know already that 2 is prime. Therefore, we set 2 aside, but after that, we cross off all of the multiples of 2 that appear in our list. They can't possibly be prime because, after all, they're divisible by 2. Having done that, we collect the smallest number that remains uncrossed out at that point. Since it's not divisible by anything smaller, it must be prime. Of course, that number is 3, but this will be harder and harder to recognize as we proceed through this algorithm. We keep 3 and we set it aside because it's prime, but then we cross off all the multiples of 3, because each of those will not be prime since they're divisible by 3. And once that's done, we collect the smallest number that remains after that process, which will be 5, and so forth. We continue crossing off multiples of the smallest number at each stage until the last number that we have not crossed out is at least greater than or equal to the square root of the number n we began with. At that point, we're done because any of the numbers that remain in this list will be prime. If they weren't prime, since they're smaller than n, they'd have some prime divisor, and it turns out that one of those divisors will be less than or equal to the square root of n. That's very easy to see. So the sieve of Eratosthenes can be used to suss out all of the prime numbers from among all the integers in a systematic fashion. Unfortunately, the sieve is not a very efficient means of finding all of the prime numbers, and since Eratosthenes' time, 2,300 years ago, mathematics has come a long way. We now have many tests to determine whether a given number is prime or not, and to search for large prime numbers. Some of these tests are astoundingly fast, some of them are much more sluggish, and but much more comprehensive. Through one means or another, we've been able to discover prime numbers that have more than 10 million digits in their representation. Mind you, I'm not saying that these numbers are around 10 million. I'm saying they have 10 million digits in them. To give you some sense for the scale of such numbers, if we were to print all of the digits in, say, 11-point font on a page, and to have 70 characters per row and 50 rows per page, we'd be looking at a volume on the order of 20,000 pages or so. So you can imagine a bookshelf being lined with a mass of digits. That's listing just one number that's known to be prime. So the sorts of prime numbers that we know about are titanic at this point. We know a lot more than Eratosthenes and Euclid did. And I'd like to turn to my application in just a moment to cryptography, but there's one more topic from mathematics that we need to talk about first. It's a topic that's not directly related to prime numbers, but is interesting in its own right. And it'll give us a sense of how the algorithm will work when we start to encrypt our data in a little while. Now, the topic that I need to address right now is modular arithmetic. We can think about taking the face of a clock, an ordinary 12-hour clock, and performing arithmetic, like addition or multiplication, on this clock face. Now, most of our operations will go through in the ordinary fashion. For instance, if we want to add 1 to 1, think about going 1 hour past 1 o'clock, we do so by adding 1 to 1 and getting 2. If we want to go 1 hour past 2 o'clock, we add 1 to 2 and obtain 3. Add 1 hour to 3 and you get 4, and so forth. This is all right until we reach 1 hour past 11 to get 12. However, if we attempt to go 1 hour past 12, there is no 13 o'clock. We're on a 12-hour clock, so we have to wrap back around to the beginning. Therefore, 12 plus 1 is not 13, but rather 1. A similar computation, for instance, would show that 9 hours past 6 o'clock, in other words, going 6 plus 9, would leave us not at 15, which is the actual sum, but having wrapped around 12, we end up back at 3. So this is modular arithmetic, or arithmetic modulo 12. That's going to be the base of our operation. We can't go past 12 because that's the largest number that exists in our world. The arithmetic that we'll perform when we do the RSA cryptosystem in a little while will use a different number, not 12 in its base, but it will be the same. It will be like performing arithmetic on the face of a clock with a large number of hours. In addition to addition, we can perform multiplication on the face of a clock as well. It's a little less intuitive since we don't typically think of multiplying hours, but you can do the operation in exactly the same way. For instance, 2 times 4 is still 8, 3 times 4 is still 12. On the other hand, 4 times 5 can't be 20 because we don't have a 20 on the face of our clock, so we have to wrap around again, and we go past 12, 8 steps to 8. And similarly, and more heinously still, is 5 times 7. 5 times 7 is 35, and so we have to wrap around not once, which would obtain 23, but twice, from which we obtain the final product, 11. So multiplication works in exactly the same way as addition, stipulating that every time we wrap around to our base, in this case 12, we just begin anew. So let's turn to our application to cryptography. This is the scenario. Perhaps Alice needs to send a message to Bob. Alice perhaps she's a defense analyst or an intelligence analyst, and she's got state secrets that need to be kept secret, or perhaps she's just sending some information about her bank account or something that contains her social security number. For one reason or another, the message that Alice sends to Bob needs to remain secret. If she's sending this via the internet, it may be intercepted by a third party, and she wants to be sure that even if intercepted, the message will not be readable. Therefore, she will have to encode the message, so that when it's sent, no one can read it except Bob, who will have the means to decode it. But if we look at this from the point of view of Bob, perhaps Bob is a trusted authority who has to have access not just to Alice's information, but to information from many people like Alice. Maybe he has to process it somehow, or maybe he has to make some sense of all of this aggregate data that's coming in. So he needs to decode information that's coming from a number of different people. They only need to encode that same information. It makes sense, therefore, that the means by which we encode this data is publicly available. That is, anyone who wants to encode the information they want to send can do so with a very simple algorithm which is easily understood and the means to which are publicly available. This sort of cryptosystem is called a public key cryptosystem because the keys to the encoding process are made public. However, the keys to the decoding process will remain private, and only trusted figures like Bob will have access to the decoding process. So how do prime numbers come into this? Let's start by talking instead about how Alice will encode her message. And for simplicity's sake, we'll assume her message contains only alphabet characters. The first step is to turn each of those letters into a couple of digits. A, for instance, can become 1, 1, B, 1, 2, C, 1, 3, and so forth, until Z becomes 3, 6. Now, I'm starting with 1, 1 instead of simply 1 because, for technical considerations, it's easier if all of the letters are represented by the same number of digits. That way, all of our letters are represented by 2 digits instead of some of them being represented by 1. So once Alice has come up with a way to turn letters into digits, she takes the message she wants to send. For instance, maybe she just wants to send the simple message, hello. She takes this message and turns each of its letters, in this case H, E, L, and O, into digits, and she jams those digits together so that they form one string of numbers. In this case, H would go to 1, 8, E would go to 1, 5, L would go to 2, 2, and O to 2, 5, so we obtain a single string of digits, 10 digits in length. Now this isn't the message that Alice will send because it's not yet encoded, and this is where prime numbers come into play. We'll choose 2 numbers that are prime, P and Q, and we'll choose a third number, K, which has the property that it is relatively prime to the number P minus 1 times Q minus 1. And this is a technical consideration that I'm going to have to sweep under the rug. I won't have time to explain all of the details, but if I had another lecture to share with you, rest assured that I would be able to explain exactly where this comes from. K and P minus 1 times Q minus 1 are relatively prime. This means that they share no prime divisors in common. So for instance, if 3 divides K, it cannot be that 3 also divides P minus 1 times Q minus 1. And if, say, 5 divides P minus 1 times Q minus 1, then 5 could not divide K. So we take these numbers, P, Q, and K, and we perform some basic operations with them. The first step will be to multiply P and Q together in order to get their product. If I say, for instance, P is 31 and Q is 59, these are 2 prime numbers, then their product will be 1,829. We can choose a K value, which is relatively prime to the product that I mentioned before, P minus 1 times Q minus 1, and K equals 11 will suit us for this example. These numbers, by the way, are rather small. In practice, the numbers would be very large, and that will increase the security of the system, and I'll explain about that once we're done. So we begin with this product P times Q. Again, in our case, this is 1,829. And we take that string of characters that Alice got from her message. This is the string 1815222225 that we got from changing all of her letters into digits. And we break it up into chunks, each of which is smaller than the product P times Q. So at this point we have 4 little numbers, each of which is smaller than 1,829, and we're going to perform some modular arithmetic on them to encode them. Here's exactly what we do. We take each of those little chunks, the first one is 181, and we multiply it by itself k times. It's essentially raising it to the kth power, 181 raised to the 11th power in this case. But this would be a titanic number if we didn't reduce it, so we'll reduce it modulo 1,829, our P times Q from before. So what we're doing is we're operating as though we were living on the face of a clock with not 12 hours, but 1,829 hours instead. After the reduction, after we reduce modulo 1,829, we're guaranteed that the result is smaller than this figure. And so, performing this operation on each of the 4 chunks into which Alice's message was broken, we obtain a list of 4 other numbers, none of which is larger than 1,829. Now, this process sounds very cumbersome, and by hand it is, but this is something that a computer can do in an instant, so it's not very difficult to ask that we do this. This information, the list of 4 now encoded numbers, is what's sent to Bob. This is the encrypted message. When Bob receives this, he will have to undergo some sort of process of decoding in order to understand the message. But notice at this point that the only information we needed to encode was 2 things. We needed to know P times Q, and we needed to know K. K was the power to which we raised each of these chunks, and P times Q was the number we used to construct the face of our clock, which we use for the modulo arithmetic. Now, when I say that we know P times Q and we know K, I don't say that we know P and Q individually, and that's the key to the algorithm. If P times Q and K are the 2 numbers that are published publicly, then anyone who has access to those can encode data and send that data to Bob. But on the other hand, only Bob will have access to the individual numbers P and Q. He will make use of those numbers in order to decode the messages that he receives, and here's how. By means of a special process that, again, unfortunately I don't have time to explain in detail, Bob is able to use the numbers P and Q to obtain P minus 1 and Q minus 1, and from them a power T, another number T, which in our case turns out to be 791. This seems rather mysterious, I understand, me just pulling this out of the ether like this, but again, if I had a little more time I'd be able to explain exactly where it comes from, and the algorithm from which this T comes is very easy to understand. Once we have this T, Bob uses this power T in exactly the same way that Alice used the power K to encode, only Bob is now using it to decode. He takes each of the numbers that he was sent by Alice and he raises them to the Tth power. So again, Alice encodes by raising numbers to the K, Bob decodes by raising numbers to the T power. Each of those chunks is raised to the power T, and you probably guessed it, because we get unmanageably huge numbers at that point, he reduces using the face of our clock with 1,829 hours on it. He reduces modulo 1,829 and obtains a list of numbers that should look really familiar. The numbers he obtains from this process are precisely the numbers that Alice started with before she encoded them using her power K. So K encoded while T decoded in exactly the same fashion. So by taking the numbers that Bob gets after raising to the power T, he can push them together and make a single string and chop it up into manageable bite-sized blocks with 2 digits each and recover the message that Alice sent. So the power T that Bob used was precisely analogous to the power K that Alice used, only he was using it to decode instead of encode. Now I know that a little bit of the magic of this operation is hidden by the fact that we don't know exactly where T came from, but it's a very simple operation that can be done very quickly by computers, and therefore this algorithm is very fast and is widely used. This is known as the RSA cryptosystem in honor of Ronald Rivest, Adi Shamir, and Leonard Edelman, 3 mathematicians and computer scientists who first devised this method of encryption in 1977. The method is secure, as I mentioned before, because P times Q is published, while P and Q individually are not. The security of the algorithm rests upon the fact that if you are given a titanic, gargantuan number, and you're told that it's the product of 2 primes, unless you know what one of the prime numbers is, it is very difficult to factor it and find the other prime number. That is, factoring large numbers, finding their divisors, is incredibly difficult, even though multiplying 2 large numbers together typically is not. It's very similar to the fact that finding the square of a number is rather easy, but finding the square root is very difficult and tedious. At this point, computers are readily able to factor numbers that have something on the order of several hundred digits, maybe 1,000 digits if we're lucky. However, recall that the largest prime numbers known have well over 1,000,000 digits in them, orders of magnitude larger than the prime numbers that computers are able to factor readily. Therefore, If we need to make the RSA cryptosystem any more secure, all we need to do is use larger primes. If someday computers gain the ability to factor large numbers more effectively, as might be the case with quantum computers, we would just choose larger primes. We are continually discovering larger and larger prime numbers, and therefore, you can rest assured that the RSA cryptosystem is going to remain secure for the time being. Well, I thank you for your attention in the last half hour, and I hope that what I've spoken about has convinced you, again, not only that prime numbers are beautiful and elegant, but that they're also very useful. And I hope that you'll take the time to do a little bit more reading on prime numbers on your own and learn a little bit more about them.